You know, when you see a fighter jet streak across the sky, it's just pure power, right? An absolute marvel of engineering. But what you don't see is this huge, invisible world of rules, of tests, of painstaking agreements. And it all boils down to one single critical thing: making sure that beautiful, powerful machine is actually safe. So today, we're going to pull back that curtain and take a look at the world of military aircraft certification.
All right, so here's how we're going to break this down. We'll kick things off with a simple question, one that's surprisingly dangerous. Then we'll look at the insane gauntlet of tests it leads to. After that, we'll dig into the ultimate rulebook that keeps everyone on the same page. We'll see how different countries learn to trust each other's work. And finally, we'll wrap it all up and see why this invisible foundation, why it matters so much.
Okay, so first up, it really does all begin with a question. And on the surface, it sounds so simple. But trust me, it's anything but. So how hard could it really be to stick a new missile on a fighter jet? I mean, seriously, right? You find a bit of empty space on the wing, you bolt something on, you hang the missile. Easy. Except, no. In the world of supersonic flight and insane G-forces, that simple act is an absolute minefield. It's just waiting for disaster to happen. And hey, you don't have to take my word for it. The official military handbook puts it bluntly. It says the process of store separation is potentially one of the most hazardous activities in which an aircraft can engage. And store is just the engineering term for, well, anything you hang on a jet. That split second it leaves the plane, that's when everything can go wrong. A tiny miscalculation and bam, it could hit the tail, clip the wing, or even make the whole jet tumble out of the sky. And it's not just about the missile hitting the plane. Think about this, something called pyroshock. See, to push that weapon away from the jet really, really fast, you often use a tiny explosive charge. But that little explosion sends this violent shockwave ripping through the aircraft structure. And that shockwave can literally shatter nearby sensitive electronics if they're not protected perfectly. It's just one of 100 things that can go wrong. So how on earth do you stop these kinds of disasters from happening? Well, you force every single new piece of gear through an absolutely brutal gauntlet of tests. The whole point is to find every single possible weakness before it ever gets near a pilot. And the list of questions these engineers have to answer is just immense. I mean, it starts with the basics, right? Does the thing even physically fit? But from there, the complexity just skyrockets. You gotta ask, will the wing break when the pilot pulls 9 Gs? Does this new shape on the wing make the jet unstable when it goes supersonic? And what about the electronics? The cockpit is flooded with electromagnetic energy from radar and radios. Will the weapons brain still work, or will it just completely freak out? Now, this leads to a really interesting, kind of subtle point, but it's absolutely critical. There's safe separation, and then there's acceptable separation. Safe separation is just what it sounds like. The missile came off the plane, and it didn't hit anything on the way out. Great. That's the bare minimum. The pilot is safe. But acceptable separation, that means it came off safely and it flew exactly where it was supposed to. One is about survival. The other is about actually getting the job done. So the process for figuring all this out is designed to be smart, to squeeze out the risk at every single step, starting with the cheapest and moving to the most expensive. First, you just look at what you've done before. You use analogy. Then you fire up the supercomputers and run tons of simulations. After that, it's off to the wind tunnel with scale models. Only then, when you've done all that, do you actually put it on a real jet that's still safely on the ground. That final, crazy expensive step, the actual flight test, that only happens when you're about 99.9% sure it's all going to work just fine. And you know, the level of detail they go into is just staggering. They even analyze what happens if the weapon gets hit by, say, enemy fire before it's even launched. Is it going to be a Type I reaction, a full-on detonation that vaporizes the plane? Or maybe a Type 3 explosion, which is still bad but maybe survivable? Or a Type V, which is more like a big fire? The engineers have to know exactly what they're bolting to that wing to understand the real risks to the pilot. Okay, so this testing is obviously super important, but it leads to a bigger question, right? Who actually decides what tests are needed? Who sets the standards? How do you make sure that an F-16 that gets a new gadget in, say, the Netherlands, is tested to the exact same safety standard as one in Belgium? Well, that brings us to the next level of this whole thing. We're talking about the ultimate rulebook, at least for European military aviation.
It's a set of requirements called EMAR 21.
Really, the best way to get your head around EMAR 21 is to think of it like the ultimate building code, but for military planes. It lays out all of the requirements, all the procedures for certifying not just the aircraft, but also all the parts and even the companies that design and build them. It's the common language, the shared standard, that makes sure everyone is playing by the same safety rules.
And this is way more than just a single stamp of approval at the very end. No, EMAR 21 creates this whole ecosystem of certified trust. The aircraft's overall design gets a military type certificate, or MTC, but the company that designs it needs an MDOA, and the one that builds it needs an MPOA. Even standard parts and repairs get their own approvals. It's a complete web, designed to guarantee quality from start to finish.
This rulebook is also clutch for handling changes over the life of an aircraft, which can be decades, right? And the key thing here is the difference between a minor change and a major change. So swapping out a burnt-out bulb for the exact same model, that's minor, no big deal. But let's say you want to add a whole new sensor pod to the wing. Well, that affects weight, balance, strength, aerodynamics. That is definitely a major change, and it kicks off a whole new super rigorous certification effort. It has to.
So, okay, this works great if all the countries involved are using EMAR 21. But what about in the real world, in a big coalition? How does, say, the Italian Air Force know for sure that a new missile on a German jet is safe to fly next to? Do they have to take that jet and retest everything themselves? That would take months. It would be a nightmare.
Yeah, that would be completely inefficient, just impossible. So this is where we have to zoom out one more time to the top layer of this whole safety pyramid. We're talking about how nations build a formal system of trust with each other.
And the solution has another one of these great names, EMAD-R. Now, listen, this isn't a rulebook for planes. It's a rulebook for the regulators. It's the framework that lets one country's military airworthiness authority look at another country's system and, after a whole lot of work, formally say, you know what, we checked you out, we trust how you do things. We recognize your safety certificate as if it were our own.
And this is no handshake deal over coffee. It is a formal, painstaking process. A country has to fill out this massive questionnaire, the MARC, that details their entire system from top to bottom. Then, experts from the other countries study every page. Then they actually fly over for on-site visits to kick the tires and see it all in action. And only if everything checks out do they sign a formal agreement. It's basically a diplomatic passport, but for aircraft safety.
All right, so let's pull all these threads together. Let's look at how this all fits, from one single dangerous test all the way up to a global system of trust.
So think about the journey we just took. We started down in the weeds with the microscopic hazard of a pyroshock from one little part. Then we zoomed out to the huge system of rules that is EMAR 21. And then we went even bigger to the global framework of trust that lets different nations work together. It's an incredible system.
So why does any of this invisible paperwork and procedure matter? Well, it's everything. It's about safety, plain and simple. It saves lives. It's about interoperability, making sure allies can actually fly and fight together seamlessly. It's about efficiency, because you're not wasting billions retesting the same thing over and over. And maybe most importantly, it's about confidence. It builds the fundamental trust that modern air power absolutely depends on.
But this all leaves us with one final, pretty tough question. This whole system, as we've seen, is built to be careful, methodical, and above all, safe. But we live in an age where technology changes in the blink of an eye. So does this incredibly rigorous system risk becoming a bottleneck? Does it slow down the rapid innovation you might need to get an edge in a conflict? It's the ultimate balancing act, right? The constant tension between being safe and being fast enough to win.